Alrighty, quick announcement. And before we dive into more about linked list. And about your written test number 1 result, I will release that either later on this Friday or the coming Monday the latest. You definitely see the feedback, you see the results, and if you got any questions about how to solve particular question, come to my office hour. More than happy to engage, to talk to you about it. And for your assignment number 1 about the recursion, I'm also going to make some solution video to you. I will try to do that within the next couple of days, and then I'll include the links for you. Right? So these are the 2 things you can expect. And for your assignment number 2, it's going to be a very important exercise for your upcoming programming test 1. So I'm going to also make it available, either by the end of today or hopefully tomorrow. Right? There will be some short pre-study you will have to do to really get used to how to create a generic list. And that's something I will also include resources for you. All right? So either, let's say by Thursday. Right? So that's what you can expect. All right. And let's now go back to the usual business about contents. And so last time we were talking about this slide here to give you some very brief and conceptual introduction about linked list versus array. And you will see more and more, as you see more and more coding example, you will really see why the linked list is so different from array. You ought to know the pros and cons for the performance between these 2 basic data structure. So what we said last time, the most important thing is you should really know for each link node, it has some reference to data objects and reference to the next node. If you remember the little diagram we drew over here, it's a very typical structure. Each node has 2 references. One will be pointing to data, and another one will be pointing to just the next node. And for the very last node in the chain, the next reference will just be now. So these are the 2 things you definitely should know conceptually. And then, let me see if I leave anything else. Okay, I talk about relative positioning versus absolute indexing of array. That's something I said I'm going to discuss today. Let me do it now. So here, I put something like relative positioning will take linear time, and absolute indexing will take constant time. Let me briefly describe conceptually, but that's something you will also need to know at the coding level. Let me put, so there are 2 things. One is, let me start with the absolute. So one is the absolute indexing of arrays. This is one of the primitive operations that we've talked about before. If you got an array A, you want to go to index I, assuming that I is a valid index. That one is going to take constant time. So when I say absolute, that means you have to give a concrete number over here. So this will be some integer expression. All right? That's why it's constant time. That's absolute indexing. What about relative? For relative, this might be a new idea to you. So let me explain it more carefully. Relative positioning of linked lists over here. And let's talk about the more general picture over here. Let's say you have the very first node in your list. It's called a head. Okay? Let's say it's pointing to a node over here. And that one there has 2 references. One is to some data, and the other one is to the next node over here. Okay, let me just give you a few more, and then I'll talk about relative positioning. Okay, so let's say we got another one here. All right. And we got another one here. Let me give you one more. Another one here, and so on. The chain can be arbitrarily long, depending on how much memory you have in your computer. So you can think about it's almost like unbounded number of nodes you can have in a chain. All right, so what's really relative positioning? So later on, we're going to talk about a method, like accessor on the linked list. For example, if I want to go to a particular position in the list, think about this is position 0, pretty much like an array. This is position 1, position 2, position 3. So indices, like positions, they start with 0. Now, if I say I want to go to position 3, can I just go there directly? Not really, because you don't really have any reference to this particular node. If I say I want to, let's say I want to get node at, and then over here, I'm going to pass an integer over here. So this will be the position in the chain of nodes. And this can just be another integer I, pretty much like the I over here. But now, in order for me to really get to that particular position I have no way around but doing this. I want to start with the head, and this is index 0. If this is not what I'm looking for, I should go to the next. And then this is index 1. Is it exactly what I'm looking for? If it is, I'm done. If it is not, I'm going to keep going until I get to index I. So the number of next references over here will correspond to the index value itself, which can be, in the worst case, n. So that's why it's a linear time algorithm. All right? So that's about relative positioning, which is big O of n. So important for you to see the difference between them. So absolute is going to be constant time, and for relative, for linked list, it's going to be linear. All right, guys, any question about this conceptual clarification? And we'll definitely see that again at a more coding level. But before that, you can already see how it works. Question? Yes. Yeah. Yes, it's a very good question. The question was, is it possible maybe to make some alias into maybe, let's say, halfway to the list? So that will make the maybe searching a little bit more efficient. Even if you make, let me sketch very quickly. Even if you make it halfway, in that case, it's around n over 2 index, right? Let's say for you to go here, to go to towards the end of the list, you still got n over 2 maximum to really look for. In that way, you're still boiled down into asymptotically big O of n. So it wouldn't help too much asymptotically. Yeah. All right. If no question, let me go over a little bit more conceptual things, and then we'll definitely dive into Java code for today. All right. So it's going to be OK here. The linked list does not have any fixed length, right? Unlike array. When you first create an array, you have to say something like, array, let's say integer, array A will be new, integer array, and then you got to pass a fixed length over here. Right? It's a fixed length. The beauty about linked list, on the other hand, you can have as many nodes as you like. Every time you want to add a new node, either at the front, in the middle, or at the end, you just add it. You have no constraint whatsoever. All right? But you got to watch out for the running time. OK. And then you can dynamically add elements. That's something we'll see as we go by more methods. OK, so these are just some example here. So ultimately, you're going to see how you can do some basic operation for linked list. We'll talk about quite a good number of them in the lecture. You'll get some challenging problems in the assignments. That's something you should really struggle through and then get help on. All right, so let's see. Contrary to array, we do not really keep track of all the nodes in the linked list. For example, here, we don't really know exactly how many nodes are there in the chain. Usually, a very typical way to really implement any method, you just start with the first one and try to go from there, go through the next references as you need it. All right? You don't have that much flexibility in this regard. OK, there's just another list over here. And then, OK, so now we are almost ready to do some Java coding. Okay? So given the head reference of the single linked list, for example, how do you really count the number of nodes in the list? That's just one conceptual exercise you can think about already. All right? Let's say here, this chain of nodes has 1, 2, and 3. We got 3 nodes over here. How do I figure out it's actually 3? You're going to start from here. Oh, maybe just let me answer that. It's quite straightforward. Yeah, I'll give you guys more chance to get involved when I get to the coding. I start from here, and I look at if the next one here is null. It is not. So I should really increment some counter maybe from 1. Sorry, let me say it again. I start with the head, and the counter should be 0. And then I look at the next reference. It is not null. It's really pointing to some objects. So I increment the counter from 0 to 1. I know I got at least 1. And then here, I got another node here. Does it have another next reference that's not null? Indeed. So I'll increment the counter from 1 to 2, and etc. Until I get to the node, that's the last node, which has a null reference. I know that I should really stop counting. That's roughly what's going to happen when we look at the Java code. That'll be the first method we'll have to look at carefully. Okay? What I described over here about starting from the head, you have to go through the next references, possibly within a while loop, is a very typical procedure you have to implement for linked list operations. All right. Okay. Do you guys have any question up to now? Just about general concept for linked list. And we got to look at Java code. Yes? Yeah, so I think, so the question was about ArrayList versus linked list. You're talking about the Java library ArrayList, right? Okay, it's different. Because when you talk about ArrayList specifically, you can look through the API for ArrayList. It is actually implemented behind the scene using somehow called resizable array. And I believe the resizing strategy is something called doubling strategy, which I briefly mentioned is the more efficient one in the amortized sense, in the average case sense. On the other hand, sorry, let me say one more thing. Think about the array list is more like a library class for which people already implement for you. And if you find that for your own application, that's all you need. All the methods that are supporting ArrayList can fulfill all the needs for your application, use ArrayList. On the other hand, when you are implementing maybe some new algorithm, in which case you might need some very customized operation. In that case, you may want to start with a linked list and build some customized operations on top. Okay. On the other hand, if you got your linked list, it's actually very good for implementing, let's say, specialized operations that may not be directly supported in the array list. But for you guys, for the assignments and for the programming test, everything should be built from scratch for you to practice. You cannot use any library classes. That will be a programming requirements, starting from assignment number 2. For recursion, you can use some maybe hash set, array list. That's OK. It's for different purpose. But for assignment number 2, 3, and 4, it's going to be about linked list and also linked tree. Everything should be built from scratch. Right? We'll talk about more. All right. Let's now talk about, I believe we can talk about Java code, Java implementation. Okay? Let me now go over with you the classes we need to have. And we'll start from the basic. Okay? So you'll feel comfortable later when you do the assignments. All right, the first one, let's see what classes do you need. And all the Java code I talk about in class, I will also make them available to you. So what you should do is import them into the Eclipse and then play with them and try to really use debugger, use other tool to really study the code. That's what I expect you to do. And there will be some assigned exercises I will also put on the slides. You can also try to build on top of the project you import. So that's kind of the extra exercises you can do. All right, let's talk about what classes we have. We have 2 classes here. One is called SinglyLinkedList. The other class is called Node class. Let's start with the Node class first. Okay? Think about node is the most basic units in your chain of nodes. It's a node, right? Think about the node. This is a node. This is a node. This is a node. But collectively, they are called a singly linked list. That's how you can make the distinction. All right, let's take a look. The node class over here, let's see what we have. We have 2 attributes here and here. Right? You can see they are private. We got elements, that's like the data. We got the next reference. You can see this type over here is the same as this type. All right? It's important to note. The node here and also the node here. Notice that they are of the same type. That means for each node, you can always point to the next node and the next node and the next node. All right? And we have a constructor over here. And the constructor is going to take the data and also the next node reference, and then initialize the attributes accordingly. And these are the methods that are really basic, but we're going to talk about them one by one. Okay? So how you can get just the elements. Oh, actually, sorry. These are rather simple, accessor and mutator. How do you just return the data? How do you set the data? How do you get the next reference, right? And also how you set the next reference. So these are all the basic accessor and mutator you should really know. But typically in the assignments and in the programming test, this entire class will be given to you. You don't need to type it out from scratch. That's the basic you can reuse, no problem. But what's going to be tricky is how you can build things on top. That's something we'll talk about. All right, just keep that in mind. All right, let's visualize very quickly a node. At a runtime, if I have a node class, it's going to look something like this. And I will make also trace some code together with you about creating nodes and linked lists. But for now, think about every node object has two attributes, element and next. So one will be the elements, and the other one will be the next. And think about the element here is going to point to some string. Right, since we are talking about the string list. Okay, oh, sorry, here's string, elements. And the next over here is going to point to some other node. It's a quick visualization about how a single node would look like. At the runtime, you might have a chain of nodes connected together. We'll see how to build it. The second class we need to look at will be something called SinglyLinkedList. There could be some confusion about why do we need another class over here, given that we can already build a chain of nodes like this. Okay? The reason is there should be some additional attributes we want to keep track of the linked list. That's something we'll see. That's why we just need another object over here, and it has an attribute called head. And that head is going to point to the first node in the chain. That's what's going to happen. Okay? It's going to actually turn out to be very valuable. But let me go over with you that class first. So we have a separate class called SinglyLinkedList over here. And the only attributes we have is here, head. All right? And what about other methods? Very straightforward. You can set a head. You can get a size. That's something we're going to implement. You can also get a tail. You want to get a last node. That's what we call the tail, which is going to return to you a node. You can add some new node storing this particular string as the first node. You can try to get a node at index I. It's a little bit like array indexing. But this one is going to be relative indexing rather than absolute. And we can add a new node storing string data E at a particular index. So this one here, I would like you to compare with how we can insert into an array that we spoke about maybe last week, or I forgot, maybe last week. And you can also try to remove the last node in the list. So these are the simplest or the most basic operations that we'll talk about most of them in class. And once you know about how to operate for each one of them, you should be able to get started solving some challenging problems, either in the assignments or in the interview site that I suggested to you. Right? That's all have to be done by you. Okay. Let me visualize one more thing for you. SinglyLinkedList, what's going to happen is at the runtime, we're going to have an objects. Okay? And the type of the objects, usually I'll just say SinglyLinkedList, SLL. There's only one attribute for now, called a head. Right? And this one here stores the reference of some node, which is linking to this particular class. For example, we might say it's going to point to this particular node. So this is what's going to happen at the runtime. We got two kinds of objects. Typically, we wouldn't play too much with the SinglyLinkedList, once we have set a head to this node over here, that's pretty much fixed, unless we have to do some operation that's going to change the head of the list. Otherwise, we're mostly going to operate at the level of the node to see how we can change the references. That's something we're going to focus on more. All right, guys, I'm going to pause a bit to see if you guys got any question. These are the minimum of the classes you have to know and to know how to build things from scratch. We'll see example. Question?
Yeah, okay. For the node, why don't they have perhaps
Like an index?
Yeah, just like an integer.
Okay. So at the node level, we only got either the data or the next one. Right? If you really want to keep track of, for example, how many nodes so far has been added to the chain, it should be up to this level of the SinglyLinkedList. That's something we'll talk about. Yeah. And also, there will be another one. Here, we are keeping track of the head. Also, we can keep track of the tail of the list. It might be also useful sometimes. But any additional information you want to keep track of about the chain of nodes, they should not be defined at this level. It should be defined at this level. That one is meant to be the centralized database about what we have, for the chain of nodes. You mean, yeah, so you will see that, yeah, we do have one slide to explain. So sometimes you want to add some additional spaces for storing some extra information to actually save some time when you do certain operation. Indeed, a look ahead is called we are trading space for time. Yeah, we'll get there. Very good question. We'll get there. All right, guys, let's now dive into, first of all, how we can construct a list. All right, and then we build you up. Okay. All right, so let's now talk about this one here. That's also on your slides. Okay. Let's say this is the node class. Let's first of all see how we can construct a chain of nodes first. And we'll see how to build a list on top of that. Okay. There are two ways for you to do it. I'll show you both very carefully. Okay, that's a basic. Just recall the constructor for a node. Okay, that's the constructor we're looking at. Given the data string and also given the node reference, we're going to initialize the attributes accordingly. All right? One way to build a chain of nodes is as you try to create a new node over here, you can pass some known reference already, if you know what it is. That's approach number one. Let me show to you. Okay? Let's say, let me just try to color them carefully. Let's say green here, blue here, and maybe not orange. Let's say, how about purple? Okay, and we got to do it in this sequence. Okay, let's start with the first one. How do I trace this line of code? I'm going to have a reference called Tom. Tom will point to a node object over here. And if you recall, every node object has two attributes. We got the elements, we got the next. And you can see over here, we got elements to be Tom. And for the reference, it is null to begin with. I already know the order that we're going to build, so that's why I drew it to the end. But in general, you may not know. Setting the initial reference of the next to be null doesn't really mean you want to put it as the last node, not necessarily. Okay? But for now, it's okay. The second one, how about mark? So mark will point to a similar node object over here. Okay? And then has the data, and here has a reference over here, right? Let's be careful. So we have the node over here, and let's set the data first. That one's the easy part. So we got elements, we got the next. So this one here is mark. And what about Tom over here? Let's be careful. When we try to execute this constructor over here, we're basically executing this constructor, right? And Tom over here is going to replace the n over here. And n over here is going to be Tom, right? That's what we're doing. And then implicitly, there is a this dot next, right? That's what you learned in 2030. And what's this? Mark. because we are creating this particular object for Mark. So Mark is the context objects. So it would be as if we say Mark.next will be assigned to Tom. So now let's see what you will do. Mark.next is assigned to Tom. That's what it is doing. All right, let me draw that, and you guys tell me if you feel uncomfortable about tracing this. This is the most fundamental operation you have to do all the time by setting references. Everybody's okay? Don't be shy. If you really got trouble with this, you got to ask me now. Everybody's okay? Okay. And the next one will be done in a very similar way, right? Alan. So Alan is going to point to another node object over here, all right? Similar structure. Node, and then here we got elements, we got next. Element here is just Alan. And what about Mark over here? So we are executing this constructor for the second time, for the third time actually, but for this time, N will be replaced by Tom. So it will be as if next will be assigned to, rather than Tom, is going to be Mark. All right, what's this? This will be the current objects, which is Alan. So what this will do, what this line will do is it's going to assign Alan.next to be Mark, which is the argument over here. All right, let me finish the diagram, and then I can take question if you have. That's how we build a chain of nodes. I would say this approach here may be less preferred by the beginners because you ought to know what exactly to pass over here. But if you already know the references, feel free. All right? Question? Good question. Is Alan the head of the chain of nodes? Not necessarily. Because here we haven't really created a SinglyLinkedList object just yet, so we don't really know. It may be, or it may be not. Okay? You only know that the chain will start from here when you actually set the head of the SinglyLinkedList to be that particular node. We'll see. Okay? Guys, I have a question for you. Quickly, quick check. All right, so let's say this. Let's say I want to somehow reverse the order. Let me put it down first. Let's say what I want to build is something like that. Rather than Alan, Mark, and Tom, I want to have Tom, Mark, and Alan. Okay? I want to have Tom followed by Mark, followed by Alan. Let's say that's what I want to have. All right? And then, so what I will do is I'm going to say, start with Tom. You can see this here. Will be new node. And of course, the contents will still be Tom over here. And what I really meant to put after Tom will be Mark. So rather than now, I'm going to put Mark. Okay? And then after that, I'm going to set the Mark. After Mark should be Alan. Node, Mark. Let me be complete. You can also try this out in Eclipse. I do encourage you to try. The contents will be Mark. And then after Mark, I should really get Alan. And then the node, finally, Alan. After which, there should be null for the next. Let me finish that. Alan. And then this will be null. So my intention is, rather than having Alan, Mark, and Tom, I want to have Tom, Mark, and Alan. This is the code I'm writing to construct it. Stare at this one here. Do you think this code will work? Give me a moment. I'll just box it so it's clear to you. Will this work? No? For what reason? Is it a logical error or something else?
Like when you call
Yes, that's exactly the point. All right, guys? Logically, you might think this makes sense, but I want to point out to you, this approach number 1 has a very important essence over there, spirits of it. You can only refer to a node when it has been created already. But here, for example, if you try to do, let's say you're referring to mark over here, but mark was only created after it has been used. Is it even allowed in Java? No. You have to create an element, you have to declare a variable before you can use it. All right? That's something I want to mention, just in case. So this one here, even though you might be thinking you know what you're doing, but does not even compile. All right? That's approach number 1. Any question? We okay? Yes? Which one? You mean the, okay. Line 3, you mean over here? Over here. Okay, I say, in the Java, you mean Tom here? Over here? Oh, okay. You mean here, right? Okay, let me see. Yeah, thank you. I appreciate it. You're absolutely right. Absolutely. I really meant to write mark. Thank you. I appreciate it. Absolutely. Yeah, you save your classmate from confusion when they watch the video. Absolutely. Very good. All right, guys, any question about approach number 1, please? We good? Okay. If you don't feel comfortable just yet about this one, I have approach number 2 for you. That one will be what I recommend for the beginner. Okay, let's see. For approach number 2, the idea is simple. Why don't you create the nodes individually with just now, next reference. And then once you created those nodes, try to set the next one by one. That might be easier for you in the beginning. Okay, I'll show you. This part over here is going to be very similar to what we did before. So for this part, let me just draw them very quickly. Okay, so we create 3 nodes. So we got Alan, which points to a node over here. Node, we got elements, we got next. Okay, over here. And if you don't mind, I'm going to copy this, save some time. And the element will be Alan. And the next will just be null. Okay, I'm just going to say these 2 horizontal bar just to represent null. What you want to write now, that's fine too. And then I'm going to create another one, which will be for mark. So this is another node for mark, right? That's the second line. And the element will be mark. And the next reference will be, I can put null over here, right? What about the third line? That one there, I'm going to create Tom. And that one there. And that'll be Tom, and then also pointing to null. Are you guys okay with what I've done so far? Right? So far it's clean, right? Up to this point, the 3 nodes have no connection whatsoever. The next 2 lines are critical. We're actually going to set the references properly. Okay, let's now take a look again. Let's trace that for the very beginning. For this line over here, Alan is the context objects. Mark is the arguments. So when we go to the set next, which is over here, think about implicitly there is this keyword, this.next, right? Let's see how things are going to work. So context object for this case will be Alan. Mark is going to replace n. And it's going to replace n. So it would be as if we say Alan dot next is assigned to Mark. It would be as if, right, for this instantiation. So Alan.next is going to assign to wherever Mark is pointing to. That's what's going to happen, right? Rather than pointing to null, it's now going to point to over here. Are we okay with this? Question?
So if you're doing exam using like Alan set next to Mark, but you see how the March node is like the second one in the graphic group. Does it have to be organized that way, or like?
Yeah, I see what you mean. If the exam, say, I give a piece of code, I want you to draw the diagram, afterwards, it does not need to be as organized as I'm doing here. If you simply got all the objects down, but the pointer is kind of flying around, that's okay, as long as they are pointing to the right objects. That's fine. Yeah. But I normally wouldn't ask you to draw this kind of diagram in the exam. I think this diagram here, I'm doing that because it's important for your understanding. And later on, when you program in the programming test, or maybe in the assignments, sometimes you might find drawing such diagram helpful to understand what you're doing. Yeah, typically I don't ask students to draw diagrams. It's hard to grade anyway, so we don't do that. Right? Okay, second line. Okay, let's do that. Mark.set next Tom. Right? So you can see now, this will be replaced by Mark. Also, argument n will be replaced by Tom. So it would be as if we said, it would be as if we say Mark dot next is assigned to Tom. So Mark dot next is now set to Tom, the same objects, right? The two approaches achieve the same thing. This one here and this one here, they are identical chain structure. Okay. And just for what's worth, about aliasing, if you think about it, I'll give you one example. What you guys learned about aliasing back in maybe 1022, 1021, or 2030 in the previous OOP course. Aliasing means for the same objects, you got multiple variables storing its address. That's aliasing. Okay. I'll just mention here. And objects reference being stored in multiple variables. Okay, now let's do some exercise together. Look at this object over here. How many variables or how many paths can we actually go to this particular object? How many? Let's get clear how many, and then we'll write them out. How many? I can give you one. Tom is referring to this object. Any other? There's at least another one, right? Is it possible to go from Mark? Mark dot next can also go to this object, right? Is there another one? Indeed, right? Alan dot next also go to here. All right, so that's aliasing, guys. All right, important as well. Okay. Number one, you have just Tom. Number two, you have Mark dot next. Number three, you got Alan dot next. So that's called aliasing. These three paths store the same object reference over here. That's aliasing. All right. A very typical question I like to ask would be, I give you some fragment of code setting the references around, and I said, okay, for this particular object, how many variables or paths are storing the same object reference, like what I'm mentioning here? As long as you know how to draw the diagram, you should be okay to figure out. All right. Okay, I would suggest we do two more examples very quickly, and then we can get on to defining methods after the break. Just bear with me, maybe about 5 more minutes. Okay. So far, we talked about, given the node class, how you can construct a chain of nodes. Okay. And what's really remaining is, how can we create a singly linked list object that points to a chain of nodes as its head? It's actually pretty straightforward. Let's see. And The way we're going to do it is like this. There are also two approaches, simply because we got two approaches to create a chain. So take a look at this. This part over here is approach number 1 of creating a chain of nodes that we spoke about before. And this part over here is approach number 2 that we just spoke about, right? You can create a chain of nodes in either of the two approaches. From there, you can set the head of another singly linked list objects. How do we do that? Okay, let's see. If you don't mind, I'm just going to make some copy here. Oops, sorry, I don't want to cut. But that might be okay. Okay, let's say we already got this chain of nodes over here. Okay, I'll make it just visible over here. Right, remember the chain of nodes? We got Alan, we got Mark, we got Tom. That's a chain of nodes that we can create from here. Similarly, we can also get the chain of nodes over here. I'll just put it down first. And then I'll talk about the extra stuff we're going to do. And then I'm going to change that to orange. All right? So far, so good, right? Nothing new just yet. And there are two lines of code that we're going to do. Number 1, we want to create a singly linked list objects, right? So that one there is going to be a list reference pointing to a singly linked list objects. So this will be a singly linked list. Singly linked list. And there's only one attribute, as I mentioned before, just the head, just for now. We might add extra attributes to the singly linked list level a little bit later. So this one here will be the head, right? Initially, when you first create using this default constructor, this will just initialize the head to the default value, which is null in the beginning. All right, in the beginning. And then we want to do another line over here. We say the list set its head to be Alan. That's pretty obvious. So head, rather than pointing to here, is now going to point to wherever Alan is pointing to. Are we okay so far? The only extra stuff we're doing is, on top of the chain of nodes, we're saying that this particular node should be treated as the head of this singly linked list objects. That's what we're doing. And if you guys remember the aliasing over here, right? Let me do this. I can now expand. Okay, I'll say go back to the previous page on aliasing. Now I can add one more. We were trying to refer to the possible path referring to Tom. How can I add one more? List the head, the next, the next. Agree? Okay, let's do that. And this one here, okay. Number 4. C, also the next page, right? You can say list, the head, the next, dot, next. Now we got 4 possible paths pointing to the objects, right? Yes. Yes, of course. Yes.
So let's say we do get node at 0.
Yeah, so you're moving a little bit ahead. The question was, if I say something like to say list dot get node at, let's say 0. Let's say that's what you write. That one there is going to refer to the first node in the list, which will be this node, starting from index 0. If I say list dot get node at maybe 1, in that case, it's going to return this node. But we're going to see exactly how to implement this. This turns out not to be a very cheap operation for linked list. All right. Yep. All right. If no question, I'm just going to move on over here. Okay, this one here is pretty much the same. The only difference is how you actually create this particular chain of nodes. But these two lines are just the same. Okay, just about how you can create the chain itself. We got two approaches. But the way you can set the head of the list, there's only one way. All right? Okay, so this point over here, identical to approach 1. More precisely, these two lines, they are the same. All right? So that one there, you can simply look at the visualization over here. And you can feel free to draw by yourself just to add this singly linked list object, and the head should really point to over here, the same. Okay. All right, guys, any questions before we can take a break? Yeah, I think usually for the very basic, I got to do very slowly. But as we build up more familiarity, I can be a little bit faster. Question? Go ahead. You mean, are you talking about this line here?
Yeah, if you put out about 7x mark after that, are you allowed?
Yeah, you can do that, for sure. So the question was, let's say, okay, I see what you mean. What you can do instead is something like this. Let's say this. If I say node, I'll sketch a bit. Alan will be, some node over here. And then I can now create, I'll say SLL for singly linked list over here for short. And then I can say the list will be, whatever this needs to be. And then I can already set right away list.set head. And this one is set to be Alan. Absolutely. What this does is something like this. Up to now, we got some list pointing to here, which is a singly linked list. And the head is just pointing to the node that's also being pointed to by Alan. So this is a node object. So we got elements, we got next. All right? Element is Alan. And the next will be, at the moment, just null. If you only got these 3 lines of code, that's what you have, right? So if you want to build up further, you can definitely do it. You can say, maybe after this one here, I want to do, maybe after these lines, I want to say maybe Alan, I want to create maybe a node, Mark, and also node, Tom, and etc. And I can also say maybe Mark the set next and Tom the set next and etc. Right? That one there is going to add to say rather than here, it's going to have another node over here and then another node over here. That's what you can do instead. Yeah. So there are many ways to implement the same thing. Yeah. It's a good question. Yeah. So guys, I think your classmate just asked a very valuable question. Let me recap. This is definitely one way for you to put things together into this particular structure over here. But there's another way I will also encourage you to try. What you can do is you only try to set the head to be the single node over here. And then from there, you can build a chain afterwards. That will also work. Okay? You're just programming, right? Alrighty. So I would suggest let's now take attendance and then take a short break. Okay? And then we can get on to some operations. Okay. Start the class. Sorry, bear with me. Yep. There we go. The poll. And start. All right, you can now check in, please. Yeah, any issue you might have, please come forward, and I got a sign-up sheet for you before I close it. Everybody's good? Yeah. come forward, please. You got it? All right, good for you. All right, guys, please take a 2 minutes break. All right, and then we'll talk about implementing some methods. Yes, I'll be with you. Give me one more. Yeah, question.
Question about like how these data structures were originated, just to get more of an appreciation. Is it simply like somebody came up with it and then worked and then it got like adopted by more people in the industry, or?
Oh, you mean to actually build from scratch?
Yeah,
Or yeah, I would say, it's a very good question.
It was created in 1955. And it's like, did somebody like stumble upon it?
Yeah, I see what you mean. Yeah, I think at this level here, because you guys are just learning about how to build data structure, so it's good to start from scratch. Yeah, but I would say to be very practical. Let's say you graduate, you got a job. Whenever you want to solve a problem that requires some very routine operations, in that way, you don't really want to build from scratch. You don't want to reinvent the wheel. You want to see there's any API that might support this. You can just reuse it. But knowing how to build things from scratch is really, at the very rare cases, let's say the operations you want to implement, there's no such API that support it. In that way, you are the one to implement it. You want to make sure you can do it. Yeah.
I guess this is how they came about.
Yes.
Somebody needed a tool for a job which they couldn't find, so they had to.
Exactly. Yeah, exactly. Maybe your supervisor say, okay, we want to build a very specialized library for our maybe machine learning algorithm. In that way, you may have to build it by yourself. Right? Yes. Yeah, of course. Absolutely. All right, guys, let's wait for 1 more minute, and then we'll get started again. Yeah, there you go. Awesome.
Yep, thank you.
No problem. All right, we'll restart in just 1 moment. All right. Oh, guys, another thing to mention. Sorry, I forgot. I should have put it in the announcement. Okay. So just about making up the time for your Monday's test, right? Since you guys were taking a test, we didn't have a lecture. So what I'm going to do, as I said in the first day, I'm going to release some lecture video for you guys to watch. And then I promise it's not going to exceed your actual normal time, about 1 hour or so. Okay. So this is what's going to happen. I'll just mention that briefly. Okay. So to make up the time, the test time on Monday. So some videos will be released.
Will they be on because of your site?
Yeah, I'll reach out to you, don't worry. It will be on the normal lecture side. I'll make it very clear about what you should really watch. About 1 hour, maximum 80 minutes, just a normal class time. Okay, so these videos, these videos will be assumed by next Wednesday's lecture, not Monday. So you do have 1 week to catch up with the material. Okay? All right, that's something I will reach out to you very soon. So you do have enough time to really watch the video. And of course, you can ask me questions during the office hour. All right, so let's now solve our very first problem about SinglyLinkedList. Very simple, but I think it can also teach us many things. Okay. The problem is we want to say return the number of nodes currently stored in a SinglyLinkedList. All right? We want to count the size of the SinglyLinkedList, basically. All right? Let's say this. Let's say this is the list structure that we have constructed, before the break. This will be the chain of nodes. And then we have a list whose head is set to the first node over here. So if you try, let's say, list dot get size, that one there is going to return back to you 1, 2, and 3. That's the method we want to implement. Pretty easy, but it does require some thought and about tracing. I think for this very basic one, you want to learn about how to trace a linked list algorithm. So later on, if you have to implement a more complicated one for your assignments or the programming test, you would know how to deal with it. Very important, all right? And let me see if I'll just directly go over with you the code. Right, so the very critical insight, which we mentioned before, you basically want to keep counting until you reach the very last node in the chain. And that very last node has the next reference being null. So that's the critical insight, all right? Let's take a look at the code, and then we'll do some tracing. And by the way, this method here is a SinglyLinkedList method. SinglyLinkedList method. This is not a method you're going to declare inside the node class. No, SinglyLinkedList, right? If you look at the class declaration that we spoke about, you will see the getSize method there. And let's take a look briefly, and then we'll try to trace it. You initialize some counter size to be 0. And a very common pattern is to declare some current reference to say, this is the current node we are looking at an iteration. Between iterations, you have to move this current reference to the next one, to the next one, to the next one, until you're not supposed to move any further. Right? This current here is very typical for any advanced implementation for the linked list operation too. Right? We're going to say while the current is not equal to null. That means we can keep moving. Right? So think about the negation. When we put the while loop over here, this one tells you the loop is going to exit when this particular Boolean expression evaluate to false, meaning that current should be equal to null. Right? Let's get the logic clear. Okay? All right, let me highlight it for you. Are we okay with this? It's really important to know. All right? And then what do we do inside the loop? Basically, we just keep trying to move the current to its next. And then we just keep incrementing size until we should not. And finally, we can return the size. A very simple method here. That's why I'm treating that for the first one. However, the pattern over here, let me recap. By using some current node and then try to update the current for each iteration by moving that to the right, moving to the right, moving to the right. And also increment some counter or some objects. That might be something you have to do for your assignment. That's a very typical pattern. All right? Now, the most important thing is let's trace the code together. Right? So important. Okay? And we're going to trace exactly this method call, right? List.getSize. So the list is over here, right? Think about the list. Context object is the list over here. Let's now start with the current. Initially, size, okay, let me just use the green here. Initially, size is simply equal to 0. Agree? That's the initial value. And then the next line, we're going to set the current to be the head of the list. All right? Current is going to be the head of the list, which is pointing to Alan. Agree? So we start with Alan. Are we okay so far? That's before the while loop. And then we are checking this particular condition over here to see whether we should go into the loop for the very first iteration. Now, if you try Alan not equal to null, that one is true. Agree? That one there is true. And then we're going to go into the iteration over here and try to do one by one. at the end of the iteration, we're going to basically set the current to be its next. What does that really mean? Okay. So think about what's going to happen here. So this part over here, because the current at the moment is pointing to Alan. Let me write a little bit better. Let me say that again. Initially, we simply set the current value to be the head. So that's why current is pointing to wherever the head is pointing to. Again, aliasing. Okay? And then for the very first iteration, we're actually going to set the current to be its next. All right? So what we do here, I'll put it down here, is basically we're executing current is assigned to current dot next. Okay? Current over here is next is over here. Reassign the current to its next. That's what it is doing. All right? That means rather than here, the current is actually going to point to the mark over here. All right? That's very important. And then we're also going to increment the size value from initial value 0 to just 1. Okay, so for this part here, let me just make it a little bit more concise. You can think about after this, current will just be equal to mark. And this will be the starting point for the second iteration. All right, we're going to keep going like this for as many iterations you might need, depending on the size of the chain of nodes. Are we okay with the first iteration? Yes, question? Yeah, talk about if there's a cycle in the chain. So let's not worry too much about it just for now. Yeah. So your classmate might be wondering about the following. What if somehow you set up the chain of nodes such that, let's say, for example, after mark, you simply point this back to Alan, let's say. So you basically have a loop over here, infinite. For now, let's not worry about it. All right, for now. Okay. Very good question. All right, let's now go for the second iteration. So the current, starting from the second iteration, is going to be pointing to mark. And we're going to check this condition again, whether we should go for the second iteration. So mark not equal to null. That one apparently is true. Okay, let's go for the second iteration. That one there was going to update the current. So current should be assigned to its next, which is this object. So we should change the current to this particular object, which will be Tom. Agree? So that means after this, current will be equal to Tom. And we're also going to increment the counter by 1. Right? Let me just use, okay, if you don't mind, let me just change the color of this. So that means after this, current will be just Tom. And the size will be incremented from 1 to 2. So current is no longer pointing to here. So the current is going to point to over here. But we are not done yet. Not yet. And this Tom here will be the initial value for checking if we should go for the third iteration. So far we have done 2 iterations. Question?
Yeah, what if two nodes are referring to the same node? So let's say Alan and Mark referring next to Tom. Will the size be 2 at the end?
You mean, oh, I see what you mean. Good question. You're saying Alan here and also Tom over here, right? Is that what you're asking?
No, Alan is referring to next to Tom. And Mark is referring to Tom as well.
Okay, you're saying, okay, it's referring to here, and then Mark is referring to here. Okay. It's not. It's going to be 2, because I tell you why. Let's say this is the head reference. So this is a node. This is another node. This is another node, let's say. And somehow you're saying that the next over here is pointing to over here, right? Okay. And then, are you saying that the next over here is also pointing to here? Okay, sure, no problem. Guys, there's a very good question. Okay. What will be the size for the list? Think about how many next you will have to do. That can be initiated from the head. Okay. First of all, from head, we got some non-null objects. So size should be 1 to begin with. Following the next from this object here, you're going to go there. Without being aware, there might be another node that's pointing to here. It's not relevant. All right? Let me say that again. Since the head is pointing to some non-null objects, so it's going to be 1. That one there is pointing to another non-null objects, which is going to be 2. So the size will be 2. This one here, not very clean, but it's not going to impact the result, just 2. Okay? Good question for the size. All right, for the final iteration, we got Tom here, which is the current. So we're going to check to see whether Tom not equal to null. That one apparently is true. So we're going to execute a third iteration. All right. For the third iteration, we're going to change the current again and also increment the size. So the current is now going to point to Tom.next, which is null. The current is now going to be null right now, right? No longer here. No longer here. So the current after this iteration here is going to be null. And size will be incremented to 3, right? You can see we always execute these two. And the current is now going to be null. Should we go for the fourth iteration? The answer is no. Because when you check null not equal to null, it's going to be false. And that's it. All right? That's how it works. That's kind of the tracing you should also try yourself when we talk about other operations. I'll try to do that if time permits in class, but that's really the general picture for tracing. All right, so now let's see. What will be the running time for this algorithm? N? Sorry, who said N? Somewhere? N? Why? Mm-hmm. Yes. Mm-hmm. So true. The number of nodes over here where the last node is pointing to null. And the nature of this loop over here tells you should only stop the loop when you get to the current reference that's pointing to null. In that way, how many nodes do you have to traverse for the iterations? It depends on the size of the chain, right? That's n, okay? Another way for you to see is over here. Look at this part over here, okay? When you look at the size over here, you can see after the first iteration, it becomes 1. After second iteration, it becomes 2 and 3, and etc. This one nicely corresponds to the number of nodes in the chain, all right? So that's why it's going to be big O of n. All right? Any question? What you really need to know is about using the current and how to play with the condition over here for the loop, and also make sure you always update the current. If you don't do it, most likely you'll run into infinite loop. All right? Any question about this one here? We've got about 10 minutes-ish. I think we can do one more, at least one more. All right. Any question about what we have got so far? All right, so today, I think we can only finish about 1 or 2 operations, but I think you can at least get started with looking at a pre-study for your assignment number 2. The methods might appear very challenging at the moment, but you should really just get some simple cases done first. And then I'll give you enough time to complete it. I'll also give you a solution afterwards. All right, let's move on. The second one over here is going to be very similar, right? So for this one here, we're going to get the tail of the list. All right, so that's something we just traced. Okay, how do we find the tail? This is basically the same problem as the first one. Rather than keeping track of some integer counter, but we just want to keep track of the node we're looking at. All right? Let's take a look. Let's say this. If I got list.getTail, what should it return? It should return a node. In this case, it's going to return this particular node. That's what it is going to return. So if I try to call this method over here, at the end, it's going to return the tail over here. Basically, we want to return a node whose next reference is null. So this is the tail, conceptually. And this one, I don't need to do, I'll keep the table very clean over here for you because I think you should really practice tracing it. What I will need to point out to you is how similar it is between these two methods. As I said before, the use of current is so common. That's why you have to get used to it. All right? But let's try. So this line here, you can see this one, we're still maintaining some current reference, right? You can see the current initially just assigned to be head, the same as before. And current not equal to null. And then current equals current.getNext. So what I highlighted in green are the same as before. What's really extra? What's really different? I want to have some additional tail over here. That's a node that I want to ultimately return. Every time I have some iteration to go through, I want to make sure tail is referring to wherever current is referring to. Ultimately, when I exit from the loop, I know that current.next is null, and at the same time, tail is pointing to current. That's the one to return. How? Again, guys, this table here for the detailed tracing is left to you. I want to operate directly on the graph very quickly to show to you. All right? Let's now focus more on two things. One is about the current. The other one is about the tail. All right? Before the loop, what's going to happen is current is going to point to the head, which is here. And the tail is going to be just null in the beginning. Right? Here and also here. That's the setup before the loop. And currently, the current is not equal to null. So I'm going to execute these two lines for the first time. So now, tail is going to be the current. So that means tail, rather than pointing to over here, is actually going to point to wherever current is pointing to. And then, current is going to be updated to its next. So current, rather than pointing to over here, is now going to point to over here. So this is what happened after the first iteration. Think about the current is always one node ahead of the tail. All right? That's the first iteration. What about the second iteration? For the second iteration, because currently current is still not null, so we're going to execute these two lines again. All right? So let's do that. So the tail, rather than pointing to over here, is going to point to wherever current is pointing to. That's the tail. And then afterwards, we're going to update the current. Current is going to be its next, which is this particular node over here, right? It's going to be here. That will be at the end of the second iteration. And again, you can see the current is one node ahead of the tail. And let's go for the third iteration, because the current over here is still pointing to something that's not null, right? Let me just get rid of this so you wouldn't get confused. Okay, that's from before. Okay. For the third iteration, we're going to execute these two lines again. So tail, rather than pointing to here, is going to point to wherever current is pointing to. And then we're going to update the current to be current.next, which is null. So current at the end of the third iteration is going to point to null. All right? And given that current is equal to null, it's going to fail this condition. That means we're going to exit from the loop and return the tail, which is over here. It's more like a visual tracing. But what you guys really need to do is this table here by following what I explained before. Okay? And to be practical, when you are designing your own linked list method, should you use a table or should you simply operate on the diagram? I'll leave the freedom to you, whichever way that might work. All right? About 5 minutes. Okay? Okay, so we talk about finding the tail as well. Oh, the running time will be just the same. Think about what's going to happen here. Because when you try to find the tail, unavoidably, you have to go all the way to the end of the chain. That means how many iterations you have to move, depending on how many nodes you have in the chain. That tells you how many next operation you have to do, right? It's still linear to the size of the list or to the chain. The running time will still be big O of n. All right? The same. So what we want to do next would be about 2 or 3 minutes. Okay? Okay, so we want to do a little bit better. Okay, very quick, and then I'll let you go. The computation for both the tail over here and also to really compute how many nodes are actually in the chain. Both of them are linear time. Linear time over here. It is possible to do better by storing some attribute values at the SinglyLinkedList level to say, rather than the SinglyLinkedList object only keep track of the head, we want to add 2 more attributes there. One is called the tail, and the other one is called the size. That's what we want to do. Okay, how? Let's go over this concept over here, and then we're done for today. And why do you want to really get some dedicated attribute for tail? Let's say if you're maintaining some server's queue, right? You want to add people to the end of the queue. So that's why you want to go to the end. That's one user scenario. And why do you want to calculate the size? Because you just want to know whether maybe the service queue might be full, so you want to refer the customer to come back maybe another time. So these 2 operations are very common operations, but at the moment, based on what we traced, they both take linear time, which is not good. What we want to do is a very important principle. Sometimes you may want to trade space for time. That means I can afford to maybe use a little bit more space for objects, for my SinglyLinkedList object, but that one can save me the linear time that's going to be taken for either finding the tail or finding the size of the list. All right? And once you get the attribute over here, so from now on, we're going to assume. Let me put it here. So now for the SinglyLinkedList class, we're gonna have the head attributes, we're gonna have the tail attributes, and also we're gonna have the size attributes. Okay, what does that mean? Very quickly, that's something we're gonna assume for later. If this is our list over here, we're adding basically 2 attributes at this level, these 2. So there will be 2 attributes over here. So also we got the tail over here. Also we got the size. And I'll talk about how you can update these 2 attributes maybe next time. But for this particular example, the tail is simply going to point to the last node in the chain. Let me draw a little bit better. Last node in the chain. And then the size will just be 3. And what can we do now? What we can do is we can simply say list dot tail. Also list dot size. Both of them will take only big O of 1 rather than big O of n. Right? So this is the principle called trading size for time. We might see some other example for this principle again, but just keep that in mind. Okay. So at this point, I'll mention that maybe on Monday when I start your fresh. Thank you so much, and you can expect your assignment number 2 to be released either by the end of today or tomorrow, and then you can get started. Take care.